This is going to be on the circular functions. We can find cosines and sines of angles that are bigger than pi halves based on angles which are smaller than pi halves. For example, if I want to look at the cosine and the sine of 5 pi over 6, this is just directly across from this. So the sine is going to be exactly the same, and the cosine will be negative the cosine here, you see. So I can find the circular functions of 5 pi over 6. And similarly for these others. This one, you see 7 pi over 6, that's directly across from, well, let's see, it's directly just a reflection to the origin of this one. So you should have, both of these would be negative, whereas they're positive here. See? And how do I tell that I can get something from this? Well, this angle is pi sixths. This angle is pi sixths, you see. So this is the kind of thing we do all the time to find cosines and sines of angles that are not pi sixths, pi fourths, or pi thirds. All right, I want to prove that the cosine squared is this, sine squared is that. Cosine of 2 theta is this. Now I can simplify this. Well, I can change it really by writing it as 2 cosine squared of theta minus 1. How do I do that? Replace the sine squared with 1 minus the cosine squared, and then I get that. Similarly, if I replace cosine squared with 1 minus the sine squared, I get this. And now I can solve this equation for the cosine of theta, cosine squared of theta. It's just 1 minus the cosine 2 theta over 2. Sine squared of theta is equal to 1 minus the cosine of 2 theta over 2. And now I can find cosine and sine of half angles. So these are going to be the half angle formulas. Cosine squared of theta over 2 is 1 plus cosine theta over 2. I just showed that up here. So if I take the square root of both sides, I find that cosine of theta over 2 will be plus or minus the square root of 1 plus the cosine of theta all over 2. And similarly, the sine of theta over 2 is this. Now here's an interesting problem. The cosine of pi twelfths is the cosine of 1/2 of pi sixths. So it should be square root of 1 plus square root of 3 over 2 all divided by 2. See? On the other hand, you see square root of 3 over 2 is what? It's the cosine of pi sixths, isn't it? Now cosine of pi twelfths is also cosine of pi thirds minus pi fourths. So if I use the other identity, I get this. And now I would ask, are these, this doesn't look anything like that. But in fact, they are the same, although they don't look the same. If I square this one, I get this. And if I square this one, I get the same thing. So yeah, these are the same because this is a positive, this is in the first quadrant. So there's no plus or minus to worry about. Now I want to prove that this is true. That's easy. 1 is cosine squared over cosine squared. So I get, when I add these, I get cosine squared plus sine squared divided by cosine squared. That's secant squared. Now if I want to show this identity, I just start with the right-hand side and use the trig identities. And now you see I have cosine x sine x minus cosine x sine x. They cancel. And that gives me sine x cosine of y. There would be 2 of them in here, and it gets multiplied by half. All right, this works exactly the same way. You just do the trig identities on the right, and things cancel, and you get sine x sine of y. This one, similarly. They're all very similar. Now, here's a little different problem. Suppose you wanted to find an identity for sine x minus sine of y. Here's how you can do it. X equal to a plus b, y equal to a minus b. So that says a is equal to x plus y over 2, b is x minus y over 2. And you just say, well, sine x minus sine of y is the sine of a plus b minus sine of a minus b. Now do the trig identities. And you get 2 sine of b cosine of a, and that's 2 sine of x minus y over 2 cosine of x plus y over 2. So it's that's just a different formula that gives you the same thing here. Okay, if you know the sine of x is equal to a, where a is something between 0 and 1, find all possible values for the tangent of x. Well, let's consider it in a triangle like this. This is a, so this side would be the square root of 1 minus a squared. And so the tangent of x, would be a divided by the square root of 1 minus a squared. However, you could have the angle of interest in the second quadrant, and in this case, the tangent of x would be negative. So you'd have negative a over the square root of 1 minus a squared. And you can go on and on worrying about various cases. All right, I want to find all the values of x that make this true. Well, this is equal to a half exactly when 3x is pi 6 plus a multiple of 2 pi, or 5 pi 6 plus a multiple of 2 pi. And so the answer is x is equal to anything of this form where k is an integer, or anything of this form where k is an integer. All right, so that gives you all the solutions. Now, this is a very important technique here. It's to represent a combination of cosine and sine in terms of an amplitude and a phase shift. All right, so we're going to do that now. We'll take our function f of x here. See, there's f of x. And it will be the square root of a squared plus b squared times all this. Now, I did not do anything. All I did was multiply and divide by this square root thing. And now, this is a unit vector. If you take this thing squared plus that thing squared, you get 1. So I know it's a point on the unit circle. Cosine xc, sine of xc. All right, this is a point on the unit circle. So now, this would be the cosine of xc, sine of xc, and so by the trig identities, this inside part is the cosine of alpha x minus xc. And then I have this outside. Now you could also do it this way. You could say, well, this is a point on the unit circle, so it will be the cosine of phi, comma, sine of phi. And then, if I plug in, I'd have, what would I have? I'd have the sine of phi here, see, and cosine of phi there, and that's the sine of alpha x plus phi, and then this amplitude. All right, here's a little application. Suppose I wanted to graph this. Well, I would just have a calculator or computer graph it, and it would work fine. But in the old days, we didn't have that option quite as much. So it's useful to write it in this form here. See, I can do that because square root of 3 over 2, that is the cosine of pi sixths, and 1/2 is the sine of pi sixths. And so by the formula for the cosine of the difference of two angles, I get this. So if I wanted to graph this, I could just graph 2 cosine of x, which I know how to graph easily. It's in the chapter. And I would end up shifting it to the right through a distance of pi halves. Now, why would that be? Well, to say that this is equal to 0 is to say that x is pi sixths. All right, so that essentially will shift the graph of this. Now, here's a little harder problem, but it'll be easy with this technique. I want to find all solutions to this. Sine of x plus square root of 3 cosine of x equals square root of 3. Now I just observed that I can write this mess as 2 cosine of x minus pi sixths, and I want that equal to the square root of 3. So that would say the cosine, I should have a cosine here, of x minus pi sixths is equal to square root of 3 over 2. And so I would have, there's a missing cosine right there. So then I'd have pi x minus pi sixths is equal to pi thirds plus 2k pi, or x minus pi sixths equal to minus pi thirds plus 2k pi for k an integer. So I could just add pi sixths to both sides and I'd get all solutions. Now this would have been a very hard problem if you didn't write it in terms of a amplitude and phase shift. Okay. How can we change from degrees to radians? Well, it's very simple. Pi radians is equal to 180 degrees. So I would set up a proportion. Pi over 180 is equal to r over d, where r is in radians and d is in degrees. So this will allow me to find radian measure if I know degrees, and to find degree measure if I know radians. All right, tangent of theta plus beta. That is equal to the sine of theta plus beta divided by the cosine of theta plus beta. Then I use the trig identities. I write it like this. And now I will multiply the top and the bottom by 1 divided by the cosine of theta cosine of beta. Then I get a 1 minus the tangent of theta tangent of beta, and then the tangent of theta plus tangent beta in the top. Okay, so if I wanted to find a formula for the tangent of 2 theta, I could do it the same way. Or I could just put in, let beta equal to theta, and I'd get 2 tangent of theta divided by 1 minus the tangent squared of theta. All right, I want to find a formula for the tangent of theta over 2 in terms of the tangent of theta. We just did that for cosine and sine. So let's see if we can do it for the tangent. Well, sine of theta over 2, cosine of theta over 2, this divided by that, that's the tangent of theta over 2, so I get this. And I can multiply the top and the bottom by the square root of 1 plus cosine of theta. Now, if I assume that theta is in this interval, so there's no odd things happening in terms of sine, I would end up with the square root of 1 minus cosine squared here. That's the square root of sine squared, and that's just the sine. So you see, this is what I'd get here. Now, if I divide the top and the bottom by the cosine, I'll get the secant of theta plus 1 in the bottom and the tangent of theta here. And then secant of theta, for theta in here anyway, is the square root of 1 plus the tangent squared. So that gives me a formula for the tangent of theta over 2. Okay, now this next problem is really pretty significant. People who calculate pi like formulas like this. All right, I want to establish that tangent of 4 theta is this complicated expression here. And then I'll use it to show that pi fourths is equal to this. The reason this is significant is that this one here and that one there can actually be computed with great accuracy without a whole lot of computations. And so you can find pi to great accuracy as well. Now, I need to tell you what arctangent is. We're going to discuss it a lot more later, but this is a good time to introduce it. Arctangent of x, an angle whose tangent is x, which is in minus pi halves to pi halves. Now, if you look at the graph of the tangent, it maps this interval from minus infinity up to infinity. Of course, it doesn't get to infinity. That's not a number. But it fills up the whole real line. And it's 1 to 1 there. So you see, it makes sense to ask for the angle whose tangent is x. And you can pick any real number x. Now, that means the tangent of the arctangent of x is equal to x. All right, so how are we going to find this little formula here? Well, I'm going to use De Moivre's theorem. Sine of 4 theta is this, cosine of 4 theta is that. So what did I do? I looked at cosine of theta plus I sine of theta. I raised it to the fourth, multiplied it out, and took the stuff that sat next to the I, and that gave me this. I took the stuff that sat next to the, that doesn't have an I next to it, and that gave me this. And that's just from De Moivre's theorem, which was in Chapter 1. So if I take this divided by that, I get this. And now I would divide both the top and the bottom by the cosine to the fourth of theta. And then that gives this expression here. Now what I want to do is I want to verify that this is true. Okay? I will know that's true if I can say if the tangent of this is equal to the tangent of that. Well, the tangent of pi fourths, see, you know what that is. The sine and cosine are equal there, so the tangent of it is 1. So I'll establish this equation if I can show that 1 is equal to the tangent of all this, see, because the tangent is 1 to 1. Now, the tangent of this is equal to the tangent of this, where I replace the 1 over 239 with negative 1 over 239 and put a plus sign there. Now, I can do that because the tangent is odd, and therefore the arctangent is odd. Okay, so then this is equal to this. We just went over that thing. See, this is an angle, this is an angle, and I'm taking the tangent of the sum of those angles, like so. And now I'll apply the formula for the tangent of 4 theta to theta equal arctangent of 1/5. So wherever I see a tangent of theta, I will put a 1/5. So if I do that in here, for this piece and this piece, I end up with a rather messy expression right here. Now you simplify that expression and you come up with this, and then simplify some more and you see that it's 1. So that's why that identity is true, and this is really very useful for people that are interested in that. Now the arcsine is defined similarly to the arctangent. It's the angle whose sine, arcsine of x is the angle whose sine is x, which lies between minus pi halves and pi halves. But now I can include the right endpoints because sine of pi halves is well defined, whereas the tangent of pi halves is not. See, because it would involve division by 0. Cosine of pi halves is 0, you see. Now sine still maps on to negative 1 to 1, but it's now 1 to 1 on this restricted domain, and that's the arcsine function. Okay, now here's some problems that will be useful later, and it's good to think of them now. Suppose you wanted to find the tangent of the arcsine of x. How would you do it? Well, assuming that we're looking at arcsine of x, this is something between minus pi halves and pi halves. It could be in the first quadrant. If x is positive, that's where it'll be, won't it? And it could be in here, if x was negative, see. So I let theta equal arcsine of x. The thing that is wanted is the tangent of x, tangent of theta, I mean. Well, this length from here to here is square root of 1 minus x squared. And so if I look at the tangent of theta, it's x divided by that. All right? Now, if x were negative, you'd have the little triangle pointing down, and then you'd have to put in a minus sign. All right, so let's go ahead and assume things are x, that the angles are between 0 and pi avs, so that we don't have to fuss with minus signs. What would the cotangent of the arcsine of x be? Well, I'd look at this little triangle here, you see, and the arcsine of x, that's the angle, so this is the arcsine of x, that's theta, and x is the sine of x, okay? So then I'd have, this would be square root of 1 minus x squared. And so what's the cotangent? Well, it's this adjacent side divided by x. And the cosine divided by the sine. All right, what's the secant of the arcsine? Well, you know, that's 1 over the cosine. What is the cosine of the arcsine of x? Square root of 1 minus x squared. So that would be 1 over x. And similarly, cosecant of arcsine of x is 1 over x. Cosine of arcsine of x is square root of 1 minus x squared. Okay, assume the angles are in the first quadrant. I don't want fussiness. What's the cotangent of arcsine of 2x? Well, here, the angle, it's this, call this theta. This is the angle whose sine is 2x. Okay, so you could draw a little triangle, and this thing here would be 2x, and so you'd have this here would be the square root of 1 minus 4x squared. So I would have the cosine divided by the sine, and that would give me this. If I wanted the secant of the arcsine of this, I'm just assuming all the angles are in the first quadrant, and so like if x and y are positive and small. Then the arcsine of this is the arc cosine of this. See? By the same reasoning we've been using. So if I take the secant of the arcsine, it's the same as the secant of the arc cosine of this, and that gives me this. See? Cosecant of arcsine, well, the sine of the arcsine would be x squared, so the cosecant would be 1 divided by that, 1 over x squared. Cosine of 2 arcsine of x, well, what do we have here? Arcsine of x is the arc cosine of the square root of 1 minus x squared. And so I take the cosine of that, and that would just give me, the square root of 1 minus x squared. So if I take the cosine of 2 of these, I have 2 cosine squared of this minus 1. Now the cosine of the arc cosine of this is just this, so it's squared here, and so I just get 1 minus 2x squared. Now you should notice that this doesn't make any sense at all unless absolute value x is very small, and that's the kind of thing you run into when you do these kinds of problems. Okay, what about this one? Well, I can use the formula. The arcsine of x is arctangent of x divided by this. The arcsine of y is the arctangent of y divided by this. And so I just use the formula that we have earlier. This plus this divided by this times that, and that's it, see? And I can find the cosecant also. This is 1 over the sine of this, and then put in what these are, you see? So if I want the sine of the difference of two angles, it's the sine of this one, cosine of this one minus cosine of this one times the sine of this one, and that's what you get, see? Now you should have at least one of the, well, let's have them both be small and positive, or at least the absolute value is Can't be any bigger than 1. All right. You can talk about the arc cosine of x in the same way, except with the arc cosine, you restrict to the interval 0 to pi because the cosine is 1 to 1 on that interval. Just look at the graphs in the chapter and you'll see that. And the same kind of things can be done. And so you can go on and do many variations of these kinds of problems. And so I will leave it at that. Now, the graphs, if you look at the graphs of tangent and cotangent, they appear to be periodic of period pi. And in fact they are, because if you look at tangent of x plus pi, it's the sine of x times the cosine of pi plus cosine of x sine of pi. This is 0. This is -1. This is -1. This is 0. So you end up with this, and that's the tangent of x. Now it works exactly the same for the cosine. Now this is really a nice way of looking at the Pythagorean theorem. This is due to President Garfield, who was shot and perished after languishing for 6 weeks. He hadn't been president very long. And I think it took him 6 weeks to die. I can't remember for sure, but they kept probing his wound and introducing infection, and somebody invented the metal detector to try and find the bullet. They never found it. Okay, here we go. This is his proof, and I think it's one of probably the neatest one I've ever seen. Okay, there we have 2 right triangles, A, B, and C. So this is a right angle, so that means its angle is pi fourths. So that means this angle plus this angle is, not pi fourths, but pi halves. So this angle plus this angle add together to give you pi halves. Because remember, I showed in the chapter that the sum of the measures of the angles of a triangle is pi. Okay, now this is the identical triangle. So I have this angle plus this angle they add to pi halves. This one plus this one plus this one add to pi radians. Therefore, this angle is pi halves. So this triangle here is a right triangle, just like I've drawn it. Okay? And so now we can write down the area of this trapezoid in 2 ways. I can take A times B. See, there's A times B, divide by 2. That gives me the area of this triangle, plus the area of this triangle, plus the area of the big triangle. That's the left side. Or I could take A times A plus B. See? And then plus, and then I'd have this triangle here, which would be what? B minus A, that's the length from here to here, times A plus B, and divide it by 2. Now, if you multiply all this out, on the left you get 1/2 C squared plus AB. On the right you have 1/2 A squared plus 1/2 B squared plus AB. Subtract the AB from both sides and multiply by 2, and there you have the Pythagorean theorem. Okay, an isosceles triangle has 2 equal sides. And what I want to show is that the base angles must be equal. Incidentally, this kind of material involving isosceles triangles was being studied by the Greeks before Pythagoras. So this was like 600 BC, or that period of time. Thales did this kind of thing. All right, so here we have our isosceles triangle, and by the law of cosines, a squared is equal to this a squared is equal to that a squared plus L squared, where L is going to be the length of this base, minus 2 times AL times the cosine of theta. See? All right. And I can do the same thing with the other angle. So all this stuff cancels off, and that tells me the cosine of alpha is the cosine of theta. Now, here's the thing. These are angles in a triangle. And so these angles are both in the interval from 0 to pi, on which cosine is 1 to 1. So it follows that theta is equal to alpha. And that completes the material on the circular functions in Chapter 2.